Welcome to High Stakes Physics. Think of your Cambridge 0625 exam like a casino, but instead of cards, you're playing the examiner's game. And to win big, you need to know exactly when to hold your facts, when to fold your weak arguments, and when to go all in on analysis. Today, we're tackling one of the most conceptually massive topics on the syllabus, space physics, specifically the cosmic zoom out from our sun all the way to the Big Bang. Now, I see two types of students fail this section constantly. We've got Alex, who just overloads the paper with raw physics facts, but offers absolutely zero analysis. And then we have Sam. Sam rushes the paper, completely misses the command words, and bleeds easy marks. Today, we're fixing both. We are going to decode the examiner's mind while mastering the origins of the universe. Let's dive in.
Look at this question. If this popped up as a 4-marker, Sam would probably panic and write something vague about light being old. Alex would just dump every equation they know about optics. Both get maybe 1 mark. The real secret? You have to understand how light acts as a literal cosmic time machine. And you have to structure that understanding using the Peel framework. Point, evidence, explanation, link. Keep this specific question in the back of your mind, because by the end of this session, you are going to write a flawless, top-tier answer that forces the examiner to give you every single mark.
Here's our strategic roadmap for today's mission. 1. Inside our sun. 2. The star life cycle. 3. The scale of space. 4. Redshift and Doppler effect. 5. The expanding universe. And finally 6. Evidence for the Big Bang. We are going to break down the exact physics you need for each, along with the specific command words Cambridge uses to test them.
All right, moving into Section 1, Inside Our Sun, the engine of the solar system. This is your cosmic backyard, and it's prime territory for state and describe command words on paper 4.
So let's look at the raw data. Our sun is a medium-mass star, about 4.6 billion years old, containing over 99.86% of the solar system's mass. The composition is crucial. Roughly 75% hydrogen, 24% helium, and about 1% heavier elements like oxygen and carbon. Now, if an exam asks you to state the energy source of the sun, Alex would write a whole paragraph about gravity. Don't do that. The command word state means you just give the fact. The answer is thermonuclear fusion. It's the process of smashing hydrogen atoms together to create helium, which releases massive amounts of energy. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGSC to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Now, things get a bit more complex. The core temperature of the sun hits about 15 million Kelvin. At that insane heat, matter cannot exist as a normal gas. It becomes plasma. You might be asked to define plasma. Sam usually writes, it's a hot gas, 0 marks. The examiner is looking for specific keywords. It is a completely ionized gas consisting of electrons and positively charged atomic nuclei because it's simply too hot for neutral atoms to hold together. And here's a brilliant piece of physics you can use for your explanation marks. The gamma rays produced by fusion bounce around in this dense plasma so violently, it actually takes about 100,000 years for that energy to even reach the sun's surface.
Pay very close attention here. This is a classic explain question. Explain why a star remains stable. You need the Peel framework. Point. The star is in a state of equilibrium. Evidence/explanation. The immense inward pull of gravity from the star's mass is perfectly balanced by the outward push of radiation pressure from nuclear fusion in the core. Link. Therefore, the star neither collapses nor expands, remaining on the main sequence. If you just write gravity and heat push each other, like Sam does, you are leaving marks on the table. You must use the exact terms: inward gravitational pull, outward radiation pressure.
Next up, Section 2, the star life cycle from protostars to black holes. This is where Cambridge loves to throw in 6-mark extended response questions. You need a rock-solid structural plan.
Let's start with stellar birth. If you get a describe the formation of a star prompt, you need chronological steps. Step 1, a cold, dense molecular cloud of gas and dust begins to collapse under its own gravity. Step 2, as it falls inward, gravitational potential energy transfers into kinetic and then thermal energy, forming a spinning, super-hot protostar. Step 3, the core temperature reaches a critical threshold, nuclear fusion ignites, and a stable main-sequence star is born. Bam! 3 clear points, 3 easy marks. Don't write a novel, just hit the key physics events.
Okay, here is the ultimate trap for students, the death of a star. The examiner will almost always test if you know the difference between low-mass and high-mass stellar evolution. The magic threshold is 8 solar masses. A solar mass is just the mass of our sun. A star's starting mass completely dictates its destiny. Stars with less than 8 solar masses end up as red giants, puff away as planetary nebulas, and leave a white dwarf. But stars heavier than 8 solar masses, they swell into red supergiants, die in a violent supernova, and leave behind either a neutron star or a black hole. Memorize this split. Alex often mixes up red giant and red supergiant. That's an instant penalty.
Look at this flowchart. In paper 4, they might give you an empty version of this exact diagram and ask you to fill in the missing stages. It's a pure memory and classification test. If you trace the divergent paths carefully, you can't go wrong. Low mass goes peaceful, high mass goes explosive. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
Let's shift gears to Section 3, the scale of space. This is where your units and significant figures become absolutely critical. You cannot walk into a physics exam without this number locked in your brain. 300 million meters per second, or 3 × 10⁸ meters per second. This is the speed of light in a vacuum. It is the absolute speed limit of the universe, and more importantly for us, it's the constant we use to measure massive distances. If they ask for this value, always check if they want it in meters per second or kilometers per second. Read the unit line carefully. Sam always loses a mark by ignoring the units.
Here is a guaranteed 1-mark trick question. Define a light year. Because it has the word year in it, thousands of students write that it's a measure of time. No, it is a measure of distance. It's how far light travels through space in 1 Earth year. Think of it as a massive cosmic yardstick. If a star is 1,350 light years away, we are seeing the light it emitted 1,350 years ago. You are literally looking back in time. So state clearly, distance, not time.
Section 4, Redshift and the Doppler effect. We are getting into the high-grade boundary territory here. This separates the A-star students from the rest. To explain light, you often have to explain sound first. You've heard an ambulance siren speed past you, right? The pitch is high as it approaches and drops as it speeds away. Why? Because the sound waves bunch up ahead of the vehicle, shortening the wavelength, and stretch out behind it, lengthening the wavelength. This is the Doppler effect. If an exam asks you to explain the Doppler effect using an example, use the ambulance, but be precise with your terms. Say the apparent change in wavelength or frequency, don't just say the sound changes.
Now apply that exact same logic to light. When a galaxy moves away from Earth, its light waves are stretched. In the visible spectrum, longer wavelengths correspond to the color red. This is redshift. I challenge you to write a perfect Peel paragraph on this in under 30 seconds. Point: light from distant galaxies is redshifted. Evidence: spectral lines are shifted toward the red end of the spectrum. Explanation: this shift to longer wavelengths happens because the source of the light is moving away from the observer due to the Doppler effect. Link: therefore, redshift indicates that distant galaxies are receding from us. Boom. Maximum marks.
That perfectly sets up Section 5, the expanding universe. Because if everything is redshifted, we have a massive cosmic mystery to solve.
Look at this graph. This is data scan time. What is the core trend here? Edwin Hubble plotted distance against recession speed. The line goes straight up through the origin. In physics terms, what does that mean? It means they're directly proportional. The further away a galaxy is, the faster it is moving away from us. The gradient of this line is the Hubble constant. This single piece of data proves the universe is expanding. Space itself is stretching. If you get a graph like this, always state directly proportional to secure the analysis mark.
If the universe is expanding today, then logic, and the reciprocal of the Hubble constant, dictates that if you run time backward, everything must have been closer together. Keep rewinding, and all matter and energy converge at a single, infinitely dense point. This is the Big Bang Theory, dating back about 13.8 billion years. When asked to define the Big Bang Theory, don't just say an explosion. Say the rapid expansion of space, time, matter, and energy from a single, infinitely dense point. Specificity wins the game.
And finally, Section 6, Evidence for the Big Bang. This is the grand finale, the ultimate 6-mark paper 4 question. Outline the evidence supporting the Big Bang Theory.
You need 2 main pillars of evidence here. Pillar 1, the redshift of distant galaxies. This proves the universe is currently expanding, as almost all galaxies are moving away from us and the furthest ones are moving the fastest. Pillar 2, cosmic microwave background radiation, or CMBR. This is the literal afterglow of the Big Bang. As the early, superhot universe expanded, it cooled, and the initial high-energy radiation stretched out over 13.8 billion years into the microwave region of the electromagnetic spectrum.
This visual is a map of that very CMBR, discovered by accident in 1964 by astronomers dealing with what they thought was static noise in their radio telescope. That static was actually the oldest light in the universe, sitting at a freezing 2.7 Kelvin. So if the examiner asks for evidence, hit them with redshift to prove expansion and CMBR to prove the hot den's beginning.
So, we've gone from the core of our sun to the birth of the universe and cracked the Cambridge exam strategy along the way. Remember the 3 rules: decode the command word, apply the Peel framework, and never ignore your units and data trends. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.